and welcome to Discovering Natural Products in Ometa Flow. Natural products are compounds created by living organisms. These compounds often possess unique chemical structures and potent biological activities, making them a rich source of inspiration for drug discovery. In fact, over 65% of all FDA-approved small molecule drugs come from natural products. Despite their promise, natural products only occupies a small portion of current drug discovery efforts. Challenges identifying new natural products and producing them in large enough quantities can make this research slow, time-consuming, and expensive. In this tutorial, we'll show you how Ometa Flow can help overcome both challenges and accelerate your natural products discovery. So let's dive in. The first thing we'll do is run molecular networking. For more details on how to run a molecular network, you can check out the linked video tutorial. For today, we're going to select our samples, libraries, and metadata. The samples we're analyzing today come from seaweed. Half are from the genus Dictyota, which inhibited the growth of several cancer cell lines, while half are from the genus Laurencia, which had no effect on cancer growth. We're also including blank samples to help identify signal from background. One quick note on the libraries is that you'll notice we have our libraries split into propagated and LC. Propagated libraries are created using computational methods, while LC libraries should be based on reference standards. Both are useful, but they'll provide a different degree of confidence in the library match. Finally, we'll change the Perform MS1 peak integration setting to Yes to perform peak integration during molecular networking. Once the task is complete, you can check out the results on the task status page. We can manually check out compounds using the molecular networking browser here, but in general it's going to be more useful to overlay our bioactivity data first. To do so, scroll down to Downstream Analysis and click the Bioactivity Molecular Networking button. This will pull up the workflow with all the correct input files already selected. All you have to do is add in the column names in your metadata that contain bioactivity information. In this case, we have viability data against 3 cancer cell lines, A549, HT29, and PC3. So we're going to add all of those columns separated by semicolons. Once complete, this workflow will provide a summary table that lists the correlations and p-values for all the detected compounds. You can also visualize this data in the molecular network by clicking on the button here. To check out the bioactivity results, I like to change the node size and node color to match the log p-value of the bioactivity I'm interested in. Now you can see that our most significantly correlated nodes are in the same subnetwork, which contains the compound arachidonyl ethanolamide phosphate, or AEAP, which is a compound that's already been studied for its anti-cancer effects. While the connected nodes with really high significance don't have a library match, they are likely structurally related to AEAP because they're in the same subnetwork. But we don't have to stop there. We can learn more about where these unknown compounds have been found previously using MAST. To perform a MAST search, simply click on a node of interest and click MAST spectrum here. This will bring up Ometa's MAST input page with the correct USI already selected. I'm going to modify the default settings slightly by changing the minimum cosine to 0.6, the minimum matched peaks to 5, the MAST tolerance to 0.05, and turn the analog search on. These changes will make the search a little more tolerant and will look for common analogs based on the MAST deltas listed here. Finally, I'll change the search database to domain MAST. Then I'll click MAST molecule with USI. Once the search is done, we can check out the results. You'll see we have over 140 matches to 25 datasets. You can check out the datasets, files, and matches here, but my favorite view is the domain MAST tab here. Here you can see that this compound or its analogs have been found in various places, but most often in plants. To check out the plant results specifically, we can go to the Plant MAST tab. Here we can see that this compound was found in several species of Euphorbia and Aromophila, which are both used as traditional medicines and have also been studied for their anti-cancer effects. MAST can help make connections like this and can also help identify organisms that are well suited for scaling up production. This is especially helpful in cases where the original bioactive molecule was identified in a very slow-growing or difficult-to-culture organism. In this case, discovering that the same or similar molecule is also produced by, say, a bacillus species can greatly accelerate purification and testing of the new lead compound. That's it for discovering natural products in Ometa Flow. Thanks for watching.